Sorry. Good afternoon. We have our invite from Tatsuhiko Sato from Japan Atomic Energy Agency. He will talk us about the general features of PHITS and its applications to response calculation of solid-state detectors.
Okay, thank you for introduction. And first of all, I'd like to say thanks to organizer for inviting me this nice conference. So actually, I'm a developer of the PHITS code, so Monte Carlo code, but I'm not a specialist of SSD dosimetry. So today's my presentation. So first half is my original topic, so like basics of Monte Carlo radiation transport simulation and the general feature of PHITS. And the second part is application of PHITS to the response calculation TLD and OSL. This part mostly done by my colleagues, Hirata-san and Alessio Parisi. Hirata-san is come here, Alessio, unfortunately, he cannot attend. So I will talk about this their work in the third part and the summary. Okay, so I think most of you know about the Monte Carlo simulation, but some are really specialists of making like a crystals. So I would like to talk about what is the Monte Carlo method. So it's trace each radiation motion using random number and estimates the average behavior by iterating the simulation. For example, if one particle is going to here and cause interaction, sometimes atomic interaction, sometimes nuclear reactions, based on the cross sections and random number. And if it generates a secondary particle, it's also transport. And third generation also transport. And all of these particles go outside or stop inside the material. One history of the simulation finished. Then next history starts. And next time, the different random number makes a different result. So this time just stop and iterate the simulation again and again. So behavior of each radiation is a highly stochastic issue, and average behavior is getting closer to the realistics. So Monte Carlo method is time consuming but accurate in general. So it's much easier to show what the Monte Carlo simulation result is better than explain it. So this animation shows 100,000 photons produced from cesium-137. The blue area is concrete and the white area is air. So photon is a kind of light. So the concrete acts like a mirror. So some photons are reflected by the concrete and going to the downstream of the main structure. And if you take the average, average of the all radiation behavior, so we can estimate the mean fluence or like a shielding ability. This case only 100,000 or 200,000 photons can reach this direction. So we can say that this main structure is good shielding profile. And by the way, so this animation is the origin of the PHITS logo mark. So it's starting from here and like this one. So next animation is more like a fancy one. So recently we introduced a 3D, actually 4D track visualization function. So this is a sample animation for accelerator shielding. And radiation is invisible in real world, but it is visible in computer via Monte Carlo simulation. So you can understand the motion of Monte Carlo radiation much better than experiment. So then I want to ask one question to the audience. So as I said before, so Monte Carlo radiation transport simulation code can reproduce the motion of each radiation in computer. So can they explicitly reproduce each interaction caused by radiation? Yes or no? So if you think no, please raise your hand. Thank you very much. So if you think yes, please raise your hand. Thank you. Thank you very much. The answer is mostly no, but partially yes. So if you don't raise your hand, you are wrong. But if you raise your hand, you are correct. Because there are two types of radiation, Monte Carlo radiation transport simulation method. And one is the condensed history method, and the other is the track structure method. And the why we need two methods. Because the atomic interactions, such as ionization and excitation, occurs so frequently in material, roughly 10 to the 6 per millimeter. So condensed history method combine many ionization and excitation as an event to reduce the computational time, while track structure method explicitly considers each ionization and excitation as an event. So this animation is a trajectory of 5 MeV carbon ion simulated by condensed history and track structure method. And as you see, the actual track structure around the trajectory is so complicated. But if you use condensed history method, you cannot reproduce this kind of structure. But the computational time is completely different. So roughly 10 to the 6th order difference. So if you draw this animation, so I take roughly like 1,000 seconds just for one history of the simulation. So condensed history simulation is fast but inaccurate in nanometer scale. I forgot to say this is a nanometer, so it's quite close-up scale. So condensed history simulation is better for general purpose such as shielding or medical physics calculation, while track structure is accurate in nanometer scale but slow. So its application is limited, such as radiation biology or atomic physics. So the two types of code were developed independently historically. So for track structure code is such as Kullback, Spartrack, Alloy-Track, and the condensed history is more like a much more famous one, like MCMP, Fuka, Giant, Polypoly, EGS, Penelope, Topaz, and PHITS. So some of you heard this code name, but maybe not so many people heard this code name. And there's a huge gap between them due to the computational cost and target size. And roughly last decade, this valleys, we construct a bridge between these valleys using the same user interface, such as Giant for DNA, Topaz NBio, or PHITS track structure mode. But just sharing user interface is not enough because still the computational cost and target size issue remains. Then we constructed more strong bridge that is analytical microdosimetric function, so-called AMF, and we apply this function to the radiation biology and detector science. And today I will talk about this part. But before that, I would like to talk more about the general feature of the PHITS code. So what is PHITS? So PHITS is a particle and heavy ion transport code system. So it can analyze the transport and collisions of nearly all particles over a wide energy range from thermal to 1 TeV per nucleon using Monte Carlo methods. And it is all in one package type code. That means all contents of PHITS, such as source files, executables, data libraries, graphic utilities are fully integrated in one package. And it is available in free of charge by submitting application form via our website or OECD NEA data bank. And it has been applied to accelerator design, radiation therapy and protection, and the space environmental or detector sciences. So if you want to know more about PHITS, please visit our website. So here's the basic feature of the PHITS code. So the source code is written in Fortran, but I know that the most younger generation never use Fortran. So we don't ask you to write a Fortran code. But instead we ask you to learn how to write the PHITS input file. It's a PHITS original language in free format text. So basically you don't have to write Fortran program just for using PHITS. And the geometry is described in the general geometry, the so-called GG format. And the graphic utility is fully integrated. So 2D, 3D, or even you can interactively see the geometry. And you can deduce any kind of quantity such as particle friends, absorb dose, number of interaction, nucleus yield. You can deduce from the simulations and output data or text data, histogram, or contour map like this. And you can run PHITS on any kind of computer, Windows, Mac, and Linux. And MPI and OpenMP parallelizations are available. So MPI is quite powerful for like a supercomputer. If you have like a 1,000 core machine, you can use 1,000 cores. OpenMP is quite familiar with like a Windows or Mac machine. So recent Windows computer has like a 30 cores, so you can use 30 core for running PHITS. So here is a map of the model recommended to use in PHITS. So unfortunately, there is no like a perfect model that can transport all kinds of particles. So that means, in other words, PHITS is plays such role. So we combine many models. Some of models we develop by ourselves. Some models we imported from other laboratory. And so important point here is we also introduced the track structure model for electrons and also ions, all kinds of ions. So this is one important point of the PHITS course. So it's not condensed only for the condensed history, but also track structure method. And here is the number of the PHITS users since 2019. So we have so many users. So roughly 7,000 users from 68 countries in 6 years. And so here is the number of the users. Of course, Japan has the largest user base, but Indonesia, like Philippines, Malaysia. So we try to promote the code to Asian country, providing lots of tutorials in many countries. So here in Mexico, we have less than 10 users. So if you are interested in, so please contact me later. So I will tell you how to get and how to use the code within this conference. Okay, now I go back to the main topic, application of the PHITS to the response calculation of TLD and OSL. So for this purpose, we focus on the quenching effect of TLD and OSL that cause the saturation of luminescence efficiency observed at high LED irradiations. So this graph shows calculated and measured depth dose distribution in water phantom irradiated by high energy carbon ions. And apparently the measured dose are underestimated at the black peak region due to the quenching effect. So if you want to use this detector to the dosimetry of carbon ion therapy, you have to evaluate the magnitude of the quenching effect, which are generally expressed as a function of LED. However, the actual quenching effect should correlate with the microscopic ionization density, and the LED is just an index of it. So LED is defined as a mean energy transfer within a certain distance. So it cannot express the difference of ionization density of low energy radiation and high energy radiation with the same LED, because high energy radiation produces more delta rays to the lateral directions. So actual ionization is lower for high energy radiation. So to properly express the microscopic ionization density, ICRU defines specific energy or linear energy. They share the same unit as absorbed dose or LED, but they are stochastic quantity, and they can consider the lateral divergence of due to the delta ray production. So here is an image of the concept of the microdosimetric quantity. So each target has different Y or Z values. However, to evaluate this kind of distribution, track structure simulation is required. And this cost prevents the use of them in conventional dosimetry based on the condensed history method. So we developed the analytical microdosimetric function, as I said before. So for this purpose, first I performed the track structure simulation for various monoenergetic ions and obtained the linear energy distribution like this for different particles with different energies. Then propose mathematical functions, rather theoretical one, to reproduce the shape of these distributions and determine its free parameter by least square fitting to this data. Then we implement this function into condensed history method of PHITS. Then we can evaluate the microdosimetric quantity in mixed radiation fields. So important point is here. So here, if we use track structure simulation, we can evaluate only like a certain monoenergetic particle, but we can estimate the microdosimetric quantity in any radiation field within practical computational time, roughly 10 to the 6th order faster compared to the track structure simulation. Then we propose a response calculation on TLD and OSL model named microdosimetric DZ model. This is originally proposed by Alessio. And this model assumes that the detector is composed of numerous spherical microscopic targets with a certain diameter. And the luminescence intensity from a target can be simply determined from its absorbed dose Z. That means response function is independent of the radiation type. And the response function is equivalent to the measured dose response for the photon irradiation to the detector. So actually, this is like a kind of imaginary response function. But the important point is Alessio correlate this imaginary response function to the real response function for photon dose irradiation. And with these assumptions, the response of TLD or OSL can be estimated from the integral of the product of dose probability density of Z calculated by the AMF in PHITS and its measured dose response for photon irradiation with the absorbed dose Z. For example, if we have a measured dose response like this is absorbed dose or specific energy. And for like 1 gray, 10 gray, 100 gray, and 1,000 gray photon irradiations, like this. Then if we calculate the microscopic radiation field, and we have like a 4 1 gray target, 5 10 gray target, 5 100 gray target, and 3,000 gray target. Then with these distributions and this response function, we can deduce the relative response to photon irradiation. In this case, roughly 0.2. So this is a fundamental of this model. So important point is the response in any radiation field can be estimated only from a single parameter, that is a target diameter, if the measured dose response function for photon response irradiation is available. So next a few slides, I would like to show the result of this model. So first one is for TLD, and these graphs show the relative luminescence efficiency of different types of lithium fluoride detectors irradiated by various ions. And it's rather difficult to see, but experimental data clearly shows ion species dependence It's quite similar to the Maria presented at the beginning of this conference. So we have different response for same LED. And basically, heavier particles have a higher response if the LED is the same, because the speed is low. And this dependence can be perfectly reproduced by setting the target diameter to 40 nanometer in this case. So this is an empirical parameter. So if you set a different number, we cannot reproduce the experimental data like this. And the next one is a result for OSL. And again, we can reproduce the various ion data quite precisely. In this case, by setting the target diameter to 100 nanometer, and in general, larger target size resulting in a less significant quenching effect because the specific energy tends to be lower with larger target. And this is another result for the OSL. So under this case, we show the target size dependence. And as you see in this case, if we set the target diameter around 45 nanometer, we can reproduce the experimental data quite well. And with this size, we can roughly estimate the density of the target, imaginary target in this detector. And it should be approximately 2 times 10 to the 6 per cubic centimeter. And this number is close to the density of doped europium of this detector. So 6 times 10 to the 16 per cubic centimeter. So we can guess that the target is something related to dopant, but the microdosimetric DZ model is a kind of phenomenological model, and we cannot deduce any concrete conclusion from the mechanism of the quenching effect only from this model. So let me summarize my talk. So there are 2 types of the Monte Carlo radiation transport code simulation, that track structure and the condensed history method. And PHITS implements the algorithm for both methods, as well as unique hybrid function called AMF. And the microdosimetric DZ model, based on the AMF, can estimate the response of TLD and OSL in any radiation field using a single free parameter. But we cannot deduce any concrete conclusion from this model, and further study the necessary for the investigate the mechanism of the quenching effect by directly using the track structure mode. And this part is Hirata-san will present during the next session. That's all, and thank you very much for attention.
Thank you. Some questions?
I can probably be loud enough. Can you add magnetic fields? Yes, you can. Yes, even in the track structure mode, you can consider magnetic field. Thank you.
Right. Thanks for the very nice presentation. Very exciting.
Thank you.
My first question is, how easy it is for users to extend PHITS, like, or is it just closed?
Good question, and not just closed. So we can open the source. So sometimes user can extend the function, such as like sometimes user want to create their own source distribution. It's very complicated one. Like a simple like a isotropic source, like a pencil beam, you can easily reproduce, but sometimes not. And in such situation, you can combine the your own source generation program in the PHITS and use it in the simulation. But yeah, maybe you imagine that the Jianpo is in such sense much better because it's like object oriented, so it's C++. But we use Fortran, so you need a skill of Fortran programming, and also you have to understand roughly the structure of the PHITS code. So it's not so easy.
But as long as I know Fortran and I can extend it.
Yeah, sure. Yeah, if you know Fortran. Yeah,
Yeah.
not so difficult, I think.
And maybe a second question if we have time. For the track structure simulations,
Yes.
like you really need to go like below 100 electron volts
Yes.
for all materials, which is
Yes.
we don't have
Yes.
data. So
Yes.
where does these cross sections for lithium and
okay.
fluoride come from? Like these are density scaled from water or something? Because
Not simply density scale. For electron case, actually, we use the density scale in most cases, but there are some materials, actually, that Hirata-san will talk about the materials. So we can use the density scaling for all materials, but it's not so accurate. So we have, user can select some materials. We already evaluate a certain parameter. So then you can use it. But of course, the accuracy is not so good compared to water.
Yeah, because at some point the fact that you have a crystal lattice might change things.
Yeah, it's quite difficult, I guess. So,
all right.
Yeah, maybe Hirata-san will answer or talk about the
will
next.
Thank you very much.
Thank you.
Okay, Maria.
Sato, could you apply this microdosimetry model to individual TL peaks and get and see a difference between the low, you saw it yesterday, between the low temperature and the high temperature peaks?
Okay, so first, the temperature is doesn't matter a lot, just for except for like a very low energy electron transport, but material extension is actually the rather rough scaling. But the good point is actually my microdynamic model is developed for water, so I never thought that this model can apply to the detector science. But Alessio is really clever, and he applied the model to detector science and a very good result. So that's really surprising to me. So yeah, in theoretical view, it should not apply to the detector science, but the result is good enough. So that's a very important point.
Okay, we thank again the talker.
Thank you.
Good afternoon. Now we continue with the next speaker. So I would like to invite Jose Vedelago from Heidelberg University Hospital.